let's go ahead, let's actually formulate this method of moments. Okay, so remember my operator was L phi of r is equal to f of r, that was my operator equation, right. So, L is the funny L. So, first of all what I should do is, I have said that I am going to use the basis Bn for the domain. So, whatever function I am trying to find out phi, let me try to express it in the basis of Bn. Okay. So, that is the first thing I will do. So, how do I actually write this? Let us further assume that these Bn's, let us keep life simple, let us call the Bn's and the Tn's to be orthonormal. Okay. They need not be, but it makes math easier. So, the question is, how do I write phi in terms of B, right. So, it is some constants, but what are those constants? Inner products, right. So, I will write phi of r, I can write it as some constants, let us call them phi n, B n r, right, n is equal to 1 to n. Since it is a basis, I should be able to express any function as a linear combination of these bases, right. And now I want to find out what is known and what is unknown here. Bn is known, phi n is not known, right. So, from a function I have converted to a set of scalars phi n, right. So, to find out phi n, what should I do on both sides? Take a inner product with what? Which basis function? Some other one, right. So, if I take it with Bm r inner product on both sides, right. Since they are orthonormal, which is the term that survives? Phi n, right. So, in other words, what I am trying to say is that take my function phi and project it along each of these basis vectors, and I want to find out the length of these projections. That is what I have reduced my problem to, right. So, the unknowns now are my phi n. Similarly, I can say that for f, which is in the range, I can write it in terms of the basis vectors for that space, right. So, I can call it f n t n r, right, and f n is going to simply be given as t n r f of r. Okay. So far nothing very complicated. Is is f n known? F n had better be known, because we said that f r is known, it is given in the problem, it is a known right hand side. So, if f is known, then its projection on any known basis function is also known, right. So, unknowns are phi n and knowns are, we have B n which is known, we have T n that is known, and we have f n that is known. Okay. So, we should be very clear what is known, what is unknown, what are we trying to solve for, right. So, in this problem what are we trying to solve for? Phi n's. Once I get phi n's, how do I get phi? Put it back into this equation, that gives me back my phi of r, which is what I am interested in, right. My objective when I started with this operator equation was to find out the phi that satisfies this equation. Okay. Now, how do we get a system of equations from my operator equation? That is the question. Okay. So, if I write down, so far what have I done? So, I have my operator L. Now, phi I am going to write in terms of these guys. So, n is equal to 1 to n, phi n b n r is equal to f of r, which is n is equal to 1 to n f n t n r. Okay. Now, here is what the method of moments prescribes. Now, what it says is that in order to solve this, that is in order to get a system of equations for phi n, what I should do is, any hints? L anyway will go inside, because phi n is a number. So, this will go inside over here. So, this will become, okay, if you want to write it, I can write this as summation n is equal to 1 to n. So, phi n L b n of r, right. L goes and now it is acting on a known basis function. Okay. Now, but I want to get a system of equations so that I can solve this. This doesn't look like a system of equations so far, right? Do I have n equations in n variables? Not really. I have n unknowns for sure, which are the phi n's, but I don't have n equations in them. So, what should I do? Inner product, right? So, that's a very good suggestion. So, what is being suggested is that in this equation, what if I take a inner product on both sides with t, any t, okay. So, let us take t m. So, what does it do? So, what I am saying is now I am going to do t m inner product of the whole equation, right. The whole equation is over here. Which whole equation? This whole equation, okay. So, what does that become? So, the first term will become, so the summation will remain n is equal to 1 to n phi m T m r inner product with L b n r, right, is equal to, now the right hand side comes in, what will survive from here? Only one term, because the t's are orthonormal in fact, right. So, now what is this equation? There is a summation over here. How many, what will this, is this known or unknown? It is fully known, right. I know I chose t, b and L is given to me. So, this is fully known. What is accompanying it? Something that is unknown, that is the phi. What about the right hand side? Known, right. So, what have I got? I have got one equation, n variables, right. How many times can I repeat this process? I can repeat this n times with each of the with each of the t's, right. So, that is why these are called testing functions. I am testing the equation with each one of them, one after the other, and I am getting n equations, right. So, overall matrix equation, supposing I get something like A x is equal to b, okay, that is what I get. So, what will my A m n be equal to? So, the rows, what are the rows coming by? The different rows are being generated by choosing different what? Every choosing a different testing function gives you a new equation, right. So, every new equation is a new row or column? Row, obviously, right. So, one question, phi of m, that is right, good, yeah, this should be phi of n, yeah, right. So, A m n, the mth row will come when I choose the mth testing function, right, and what will give me the nth column? The nth basis, right. So, in fact, the A m n is already written for you on the slide. So, it is T m of r L b n of r, that is the mnth element, and what is the b m? Simply f m, right. So, b is a column vector with f 1, f 2 all the way up to f n, right. Is something confusing? Oh, right, okay, yeah, you are right. So, I should probably not call this b, that is confusing, let us call it A x is equal to c, right. So, we will say that c m is equal to f m, yeah, unless abuse of notation is the word you are looking for, okay, fine. So, I have got my matrix equation A x equal to c, and we have done this, okay. So, this is formally called the method of moments. Straightforward. Where do you think all the hard work will happen? What is so, I mean, we are going to spend a long time discussing this. Where do you think the hard work happens? Finding? Transforming B, and your answer? No, Bn and Tn I will choose something simple. I can choose pulse basis function also. If I am very lazy, I can choose pulse basis function. So, B's and T's are easy. What is the? This, no, solving the equation is not difficult. Once you form your system of equations, MATLAB does A/B, you are done. I mean, you can do research in that, but as sort of core work in computational electromagnetics, where is that effort going to come in? This, inner product over here, because L is a complicated operator. So you have to operate it on L of R and then take the on B of N and then take an inner product with T of M. So it looks very compact over here. It looks like there's not much to do over here. Well, we'll see. Okay. So what are some of the things we've done one module on numerical integration, right? So for example, when I write something like H of R comma K of R, when I write the inner product like this, what does it mean? It's an integral, right? So it's going to be an integral of H of R prime K of R prime dr prime over some specified domain, right? So what is going to happen? This guy and this guy, they have to be integrated to get you this inner product, and this itself may be an integral with differentiations inside it or whatever. So this is where all the CEM action happens. Okay. Another sort of, I am getting ahead of myself, but I will tell you one other challenge that will happen over here is that your we've seen Green's functions, right? Green's functions will appear inside here somewhere in the L operator or whatever, and these Green's functions have singularities. So we have to be very careful of integrating in the presence of singularities. Okay. So those are some of the challenges, right? So let's, as they say, put old wine in new bottle. All right. So let's look at what we have already done. This was the equation that we had, right? Now I want to describe our naive approach that we did of discretizing the integral equation in the new language. So first step was basis. So what did I choose for the basis? I mean, my variable was rho. So I wrote rho of r prime in terms of the basis functions, right? I called it, let's say, some rho n bn r prime, right? And bn was something like this. This is my r prime 1 0. This was my bn r prime, right? Nth segment. So that was step 1. So I did the basis function, right? I didn't really call it basis. I mean, I didn't call it method of moments then, but I chose a basis function then. And then what did I do? Did I choose a testing function?
That is delta.
I didn't actually choose a testing function, right? I just evaluated the right hand side at different values along this y axis. The cylinder was here. I just chose different discrete points over here. I didn't choose a testing function, right? So the correct answer has come from the audience that the testing function was the analog of a delta function. Okay. So let's see how. So what was the right hand side that we had in this equation? So this Fm that I wrote over here, how did it actually come? It came when I took an inner product of Tmr with f of r. That's how I got my Fm, right? Now what am I saying? Testing function. How do I get v of Rm? Right, exactly. So I get v of Rm is equal to integral of v of r multiplied by r minus Rm dr 0 to L. So this is an inner product. It implies that my testing functions Tm of r is nothing but a delta function. Okay. So this is the easiest or the laziest thing you could do, right? So this method that we did, it is also called pulse basis and delta testing. Some places will not call it delta testing, they will call it point testing. No, that is what. So discretizing the integral equation like what we did is equivalent in the language of method of moments to choose a delta function as the testing function. Well, Okay, so the problem is that here this is not actually a function, this is a generalized function. So I cannot talk of f of m exactly in this case. So that's why I went back and I wrote another definition for fm, right, because I cannot define the value of a delta function at some point, it's undefined, right. So another word for this is called point co-location method. You can imagine this method has been around for such a long time, everyone has come and given it a different name. Okay, so you encounter any of these things, you know they are talking about the same thing. Okay. So this is sort of what we did. If you wanted to be more sophisticated, going back to the very original question I asked at the start of the module, what would you do instead? What could you do instead if you wanted more accuracy? Not choose delta testing function. That is what we could do, right. So, we could, instead of doing this point testing, I could have chosen my Tm over here, I could have chosen Tm of r also to be the pulse basis function. I can say this is also of this form. I could have chosen this. Okay, so again, so a question is that is there any advantage of keeping these two the same? So first, it makes the math somewhat easier. It's not necessary that you have to do this. You can choose a different set of basis functions and a different set of testing functions. A little bit easier. I mean, the simplification gets a little bit easier, but if you choose different, it's not that it becomes unsolvable or whatever. Finally, you are not going to do these integrations by hand. You are going to code up something, right? So it's a one-time effort, anyways. Different choices of the testing and the basis functions give you different accuracy. Okay. One more term I am going to use, getting ahead of myself because the question has been asked. When you choose the testing and the basis functions to be the same, this method is called by the name Galerkin's method. Named after person by the name Galerkin. So if you read the word anywhere which says Galerkin's method was applied, it means the testing function and the basis function, whatever they may be, were the same. So it's not necessary that they have to be pulse basis function, they could have been triangle, anything else. Okay, so that's your Galerkin's method, which is also very popular in finite element methods.